Hello everyone. So in this lecture, we are going to talk about doublets plus a uniform flow, and we want to see how these two flows, the streamlines in these two flows together will be formed. So we will look at the streamline shapes as well as some other characteristics like calculating the pressure, how we can calculate pressure around some specific streamlines, okay? So we know from previous lecture that in order to kind of solve these two, we need to, because of the linearity of the complex potentials, we can just add their complex potentials. So we know that the complex potential of the doublet is, we derived it, is delta over z. And then we just need to add the complex potential of uniform flow to that, which is going to be uz, okay? So here we have this doublet. So let me copy it here so we see what happens when we have this doublet. Let me see if I can copy all the things here. A doublet plus a uniform flow. You start from here. Okay. So for the doublet, we have the streamlines, as we talked about it last time, are just going to be some circles in that are located, their centers are at x equals to 0 and different y's, okay? So let me just show, if we have, say, a doublet here, how does this look like? So this is kind of the shape of the doublet. And then this is how it looks like here. And then say we have a uniform flow now. We add a uniform flow to this. And we want to see how the streamlines would look like. So if you see at some point here, because we have two opposite flows, the velocity is going to become 0. And so you are going to have some streamlines that will go like this. So let me just copy here. Okay. And then the other streamlines would be going around that. So this streamline will go here and then here. And then the other ones that are farther will go like this. Okay. And this streamline, now we want to, this is kind of the qualitative way of showing these streamlines when we combine a doublet with a uniform flow. And now we want to find analytical solutions for this. So in particular, I'm interested in this in this streamline, and I want to say I want to find what is the shape of this streamline where it passes through the stagnation point. So here, we have a stagnation point here at this green point. And in other words, we want to find what is the side of psi function that passes through this stagnation point here. And the other question that we want to answer is that, is there a value of psi where it defines a circle? So we want to see whether we can kind of set the parameter space such that this, instead of this ellipse, becomes like an kind of circle. Okay, so on the circle, we know that r, the distance r, should be constant like a. Okay, and so I can just write z is going to be r e I theta, which is going to be e I theta for all theta. So on that circle, on this circle, if that's a circle, this should happen, right? So I can write the complex potentials for this around that circle as UA. Instead of UZ, I can write for this one, I can just write UA EI theta. Right, this is Z. Plus delta over Z, which is going to be delta over R EI theta or A EI theta. So I just write A as e to the minus I theta because it's in the denominator. Okay. So now I want to find psi, so I need to find the real and imaginary part of this. So I can write, instead of EI theta, I can write cosine theta plus I sine theta. So it's going to be cosine theta plus I UA sine theta plus delta over A cosine theta. E to the minus I theta is cosine theta minus I sine theta. Okay, so now I have kind of, I can separate the imaginary and real part. So psi is going to be the imaginary part of this complex potential, which is going to be UA sine theta, because again, this equals to phi plus I psi. This is just a definition of F. So it's going to be UA sine theta minus delta over A sine theta. Okay, and I just set it to 0, and I want to find, here I had to say, is there a value of delta? I'm sorry, is there a value of delta where it defines a circle, where this psi, I think I should make it like this, where this psi becomes the circle. Okay, I think this is a proper way of asking this. Okay, so now I want to set this psi to 0, and if we set this to 0, then delta is going to be what? These two sine thetas are going to cancel out, and delta is going to be UA squared. So if we set delta to UA squared, then this psi equals to 0 that passes through this streamline there becomes a circle. Okay, so we can check that. We can check it again to make sure that's the case. So say fz is uz. Instead of delta, I just write delta over z. I just write here, instead of delta, I write ua square based on here. ua square over z, which equals to u times z plus, I just factor u is going to be uz square over z. And so when psi equals to 0, then as you see, the streamline is going to be a circle with r, the radius equals to a for all theta values. Okay, when psi is 0. You can simply check it here. When psi is 0, then this is just going to be valid, right? This will be valid for any theta. R should be equal to a. And you can simply check it if you don't believe, you can simply check that. So for psi, we know that it's going to be u or sine theta minus delta over r sine theta equals to 0. So these two are going to cancel out. So here, because delta, we know it's a squared, ua squared. So ur minus ua squared over r has to be always 0. You are going to cancel out. So r should be always a here. Okay, so this defines a circle here. If we kind of set if we set the delta as ua square, then psi equals to 0 is going to define a circle with r equals a for all theta values. Okay, so now I want to go further. So this is not generally a circle. We know that. It really depends on the value of delta. But if we set delta to ua square, then this becomes a circle. This becomes a circle. Okay. So now say, okay, this is a circle and I want to find the pressure distribution along this circle. So the next thing that I want to investigate and find is the pressure distribution along this circle. So say this is a circle, and then we have two streamlines here. The streamline is going to look like this. So we have the velocity starts from here as a uniform flow in infinity, then reaches to this circle, goes around that because of this doublet that is inside it. So this is for psi equals to 0. And then after that, we are going to have this uniform flow again. Okay, so now I want to find the pressure distribution along this circle, and this is in general for any stream flow that you can, for any streamline that you can use this technique. And what we are going to use is actually Bernoulli equation. So we can write Bernoulli equation. Why? Because again, the flow here, we assume this is rotational, it's inviscid, so we can just use Bernoulli equation. Okay, so if we use Bernoulli along this streamline, what we are going to get, and you can use Bernoulli along the streamline. So we are going to get first here, for if you, this is P infinity, I just want to write it here, and then the next part is going to be somewhere inside this circle. Okay, so P infinity plus 1/2. We know here the velocity is going to be U, is a uniform flow. So the velocity is U here at infinity. So we have 1/2 rho U squared equals to P plus 1/2, and somewhere here we can just neglect. This is like let's say in XY plane you are looking from top, so there is no change in the elevation. And then plus or the changes in elevation is kind of negligible, so I don't write it down here. Plus then we have the velocity somewhere here. I just write it as rho U, and pressure somewhere there, U theta squared. And why U theta is squared? Because we know that we don't have any radial velocity here. So the only velocity that we are going to have there is going to be the tangential velocity, because we know that UR is 0 and psi equals to 0. Otherwise, that's not going to be a circle. Okay. So based on this, we can simply find the pressure at any point if we have this tangential velocity, right? So we know that the velocity is going to be 0 here. So then this is 0, so the pressure is going to be just the sum of these two at the stagnation point. So based on this, we can define what I call a pressure coefficient, Cp, which is used a lot in designing airfoils. So we define this as P, the pressure, minus the infinity pressure, P minus P infinity, over 1/2 rho U at infinity, or the uniform flow U square. This is called the pressure coefficient. And remember, this is what we call this as dynamic pressure. It's like its dimension is pressure, but it's like depends on the velocity, so we call that dynamic pressure. And from this equation, we know this is going to be P minus P infinity over 1 rho U half is going to be 1 minus U theta over U squared. Okay? So in order to further go further and proceed, we need U theta, right, to find this pressure coefficient and pressure at any point in this on this circle. So we need U theta. So let's now go back to our complex potential to find U theta. We know that Fz is Uz plus UA squared over Z for this complex potential that we have. So I just wrote it here. And in order to find the velocity U theta, we need to take the complex velocity. So we need to take the derivative of F with respect to Z, which is going to be U for the first term, and for the second term is going to be minus UA squared over Z squared. So it equals to u 1. If I factor u, is going to be 1 minus a squared, and instead of z I can just write r to e I theta, so it's going to be r squared e to the minus 2 I theta which equals to u. I can just multiply everything inside here by u. I just want to factor e to the minus I theta, so I can find the u theta and ur from here. So the first term is going to be e to the I theta times e to the minus I theta. It's just 1. And then the second one is going to be a square r square e to the minus I theta. And then I can factor out e to the minus I theta from both sides. Okay. So this is going to give me u e to the minus I theta, and then I want to separate the real and imaginary parts of this. So we have the first one is going to be cosine theta, so let me just factor cosine theta from both sides. So 1 minus a square over r square cosine theta, this is going to be the real part. And then the imaginary part, the first one is going to give me sine theta, so I can factor out sine theta, and the second one is going to be minus sine theta, so it's going to be plus a square over r square sine theta. Okay. We know that this equals, the wz equals to the e to the minus I theta ur minus I u theta. Okay, so simply we can find u theta here. So u theta is going to be the imaginary part of that times u. So it's going to be minus imaginary part of that, so it's going to be minus 1 plus a square over r square sine theta u. Okay, so now along that circle r, we know that r is going to be a, right? Here along this circle, we know that this r equals to a. The radius is a. And we know that ur is 0. So when r equals to a, this means that this is going to be 1. So u theta is going to be minus 2 u sine theta. So now we can simply find Cp here. What is Cp? U theta over u, 1 minus u theta over u squared. So Cp is 1 minus u theta over u squared, which is going to be what? 1 minus u theta over u is just 2 minus 2 sine theta, so it's going to be minus 4 sine squared theta. So this is going to be the pressure coefficient. So now I can plot this. I can plot the pressure coefficient and say where we have the highest and lowest pressure in this flow. So let me copy this. Okay. So say we start from left to right. So let's say this axis shows theta. We just increase theta. Let's say from 0 to pi, we just go this way. And then here we want to write P, the pressure. Okay. So when theta is 0, so this is theta 0, say. This is theta is pi half. And then this is theta pi. Okay, let's say we start from here. So when theta is 0, Cp is going to be what? Is going to be 1, right? So I just write it here. And when theta equals to p to pi, again, Cp is going to be 1. And in between, when theta equals to pi half, sine theta is going to be 1. And so here, Cp, this is Cp. Cp is going to be -3, right? So in between, we are going to have something like this. If you plot it for all the theta values, Cp is going to vary like this. Okay. So what's going to happen is like this. So if we have, say, this circle here, okay. So what happens is flow comes from here. Then as the flow goes up, what happens? As the flow goes up, pressure is going to decrease, right? We see it here. So pressure decreases until we reach here, P1. And then after here, so when the flow goes around this, as you see, the pressure starts increasing. So pressure starts increasing. And then after this, the flow goes here. So what we expect in an inviscid world is that the flow around this should be like this too. It goes here. Then as it goes there, we have pressure is going down. And what really happens is when the pressure goes down, means that the pressure here is lower than pressure here, right? So we have a pressure gradient in this direction, which is going to help accelerate the flow that goes around this. So we call this as favorable pressure gradient here. Okay. On the other side, when the flow goes down, it goes down here. And as it goes down, the pressure increases. So we have a negative pressure gradient. So the pressure gradient is going to be in this direction. So here the pressure gradient is in this direction because we are increasing, the pressure is decreasing. And because here pressure is increasing, the gradient of the pressure is going to be opposite the direction of the flow. So it kind of decelerates the flow. And here, because of this, we call this region as adverse pressure gradient. So this is actually for an inviscid flow. However, in the real world, we also have viscosity. So what happens here, if you have like a cylinder here and then the flow goes around it, at here, because of this adverse pressure gradient, the flow will separate. The flow will separate from this cylinder. So it goes up to here, but then, so it starts going down like this, okay? And then because of this adverse pressure gradient, it will separate from the cylinder, and it will form something else, which we call it as kind of some other vortex, which we call it one Kármán vortex sheet, and I will come through that. So here we have separation in viscous flows. This is for real world flows, where we have viscosity. And I will talk about why that happens. So in a real world flow, the CP, this is again not for this kind of idealized way. So if you don't have even inviscid world, so in a real world, the pressure is going to decrease. It will decrease up to here. And then when it wants to increase, it will not go back to its level at 1 here. Because of this viscous effects, this will go back a little bit higher, but not that much. So this is the case with a real case with viscous flow. And these losses of pressure are because of this boundary layer. These losses in the pressure are because of the boundary layer that is going to form near the surface of that circle, say, or that cylinder. We can have some viscous forces that kind of leads to these losses in pressure. So these losses are in the boundary layer. BL means boundary layer. Okay, so now let's investigate this mechanism more, because that's very important for, especially if you want to design something like a cylinder and then you want to say, or even some blades or airfoils. This is very important phenomena, which is known as separation of flows, which occurs in kind of viscous flow. So let's investigate this, how this separation occurs. So let me just plot this larger. So here you have, let's say, just that part of this circle. Or cylinder. So at the beginning, at top, what we have is this flow. Now, in a viscous flow, we know that when we have viscosity, so if we don't have viscosity, the velocity profiles will look like this, right? Everywhere they are going to be the same, okay? But because of viscosity, we have to have a no-slip condition near the surface. So the velocity at the surface has to be 0, and then it will go higher above that to the streamlines that we have, okay? So because of no-slip condition, you are going to see something like this. So this is no-slip condition. And what happens is, so we have it here. What happens is here, as you see, the pressure is increasing. So let me show it like this is Y. Let's say here. So the pressure increases. So we have a pressure gradient force that acts against the direction of the flow. So we have like a pressure gradient force in this direction, right? And we know in the I'm going to drive this actually. So let's look at that. So if I want to write the streamwise momentum equation inside the boundary layer, and by the boundary layer means when up to where we get to the u infinity here, okay? So if you write the streamwise momentum equation along that line, along a streamline or a streamwise direction, so we have, say, away from the streamline, we can have something like this. So I call this S, and then I name this Y. So I want to write it in terms of Y and S. So it's going to be U, partial U over partial S along the streamline is going to be minus 1/2 dP over ds plus nu. We also have viscosity, which we know is going to be partial square U over partial Y square. Okay. So what happens here is that now when we go here, the pressure increases along S. So the pressure gradient is to be positive in that direction, but we know because of this minus sign, we have a negative force here. So the force that is going to act here is in this direction. So we are going to have an adverse pressure gradient because it causes the velocity to decrease. So causes the velocity to decrease along streamline S and possibly go to 0 or reverse if the adverse pressure gradient is strong enough. So what happens is that here the dP over ds is positive, so we have a force that is kind of decelerating the flow along the streamline. So what we are going to have here, if we have this streamline, let's say I want to plot this streamline as we go around this. So along this streamline, the flow has to decelerate. So away from that, say, okay, it's like here. But near that, it's going to decelerate. It's going to be lower than that. And then as we go further down, let's say this one has to even further decelerate. So it's going to be like this. And would look like something like this. It can make it even 0. So as you see, it decelerates the velocity and kind of reduces that. And then as we go further down, this deceleration has to become even more. So if I want to plot it here, we are going to have something like this. Very away from the surface, we have that uniform flow, but closer to the surface, even this flow can even reverse because of this deceleration. So this is going to reverse, becomes like this. Because here we have adverse pressure gradient. Is acting opposite the flow direction, and this leads to this reverse flow is the cause of this separation, flow separation. So that's why we see this here. So the flow will separate, will go this way, and it will separate. Okay? So this is why in real world we might have flow separations. And what we are going to see for this, if you have a cylinder here, is kind of a famous trend and famous pattern, which is known as von Karman vortex sheet. If you put a cylinder and then you want to study the flow around it, so the flow here is going to go around it, and then it will kind of separate from the cylinder. So you will have a vortex that will be formed here, and then you will have another one here. And then these vortices will form something which we know as vortex shedding. So a little bit further from that, you may have something here, that another vortex that will occur here. And this is necessary to make the whole circulation zero in the system. And then another vortex that will be formed somewhere like here. And so, for example, this one is going to go around this, so we will have a negative circulation around here. And then this one is going to go this way, so we have a positive circulation, because it's going to go like this. It's going to rotate this way. So you're going to have a positive circulation. Again, here is a negative one. So we have to have all these vortices. So the total circulation in the system, the sum of that is going to be zero. It's going to be positive one. And so this pattern that is formed is known as von Karman vortex sheet. You have these vortices that kind of are forming because of this cylinder here, and also they call this as a vortex shedding too. Okay, so this was just something I wanted to add in real world flows, how they would look like. And if you hear about adverse pressure gradient versus favorable pressure gradient, what it means, and separation. So this is just an estimate here, but it's very useful when you want to design these kind of things. And so in the next session, what I'm going to do is I'm going to now also add a counterclockwise vortex to this doublet plus uniform flow. And then that would be very useful, because we can use that for some kind of designs like airfoils or other things, and define these circles such that we can kind of define the separation points such that based on what we want, and also angle of attack, and then we can calculate also the lift force around this kind of circle, which will be very useful for kind of designing different airfoils or blades, wind blades. Okay, thank you very much.